So we're going to use this to review seafloor spreading and subduction. We've talked about it a little bit already, and we know seafloor spreading happens at a divergent boundary, and subduction happens at a convergent boundary. So we're going to use these to review those today. Make sure you have your note sheet out and ready. So when we talk about seafloor spreading and subduction, it's the Earth's way of constantly recycling itself. It's going to recycle the lithosphere by sinking and being destroyed at a subduction zone, and then being reformed or new crust being formed at a divergent boundary or a mid-ocean ridge. So these are constantly in place so that the lithosphere is recycled over and over and over again. So let's look a little more closely at seafloor spreading. We're going to talk about what it is, where it happens, and what it causes. Seafloor spreading is when molten rock from the mantle is pushed up to the Earth's surface. It's going to make that lithosphere or the oceanic crust separate to make room for it. The process occurs at a divergent boundary. That area is called a mid-ocean ridge. And the reason we call that a mid-ocean ridge is because as the molten rock rises from the mantle, it's going to get cooler. So when it reaches the surface, it's going to cool off, it's going to get hardened, so it's going to become that mid-ocean ridge, much like a small mountain. The best known ridge is the one that runs through the middle of the Atlantic Ocean, and it's called the Mid-Atlantic Ridge. And it's because of the seafloor spreading. So over the millions of years, that seafloor spreading is slowly pushing North America and South America away from Europe and Africa. It causes the Earth to spread apart, and the new Earth is created. So we're having that new crust created every time the magma pushes up, makes the seafloor spread, it hardens into that mid-ocean ridge. So scientists do have pretty solid evidence to support this whole process of seafloor spreading. When they study the rock in and around a mid-ocean ridge, what they have found is the closer it is to the current ridge, the newer the crust is, because you've got the magma rising, getting hard, creating a ridge. So that's going to be the newest. And as we move away from the ridge, we're going to see older and older crust because it has been spreading out over millions of years to let that new magma come in and make the crust. They've also found that there's magnetic material that comes up with the magma. So that is stored in those mid-ocean ridges. So as they move further and further out, they can see this pattern of where the magnetic poles have switched over millions of years. That means, like if I had a compass, my magnetic north might point toward the North Pole at the current mid-ocean ridge, but millions of years ago, if I had my compass out, my magnetic north would point toward the South Pole, the geographic South Pole. And these have switched back and forth over millions of years. So as we look at seafloor spreading and we look at this picture, there's a couple clues that we have that this is a divergent boundary. We see that the arrows are moving away from each other. They're diverging or dividing. We see the magma rising. We see the mid-ocean ridge, and we see the magnetic stripes. All of those are clues to let you know this is a divergent boundary. Some extra little facts. New oceanic crust is created at the mid-ocean ridge, and we call that oceanic crust because of where it's created. It happens at a divergent boundary. The magnetism pulls the minerals in certain directions, and that's where we talked about the magnetic reversals. It happens at a mid-ocean ridge, and it's considered the longest mountain chain in the world, and it's underwater. All right, let's take a look at subduction. It's really the opposite of the seafloor spreading. We're going to talk about what it is, where it happens, and what it causes. So subduction is where two plates collide, they crash, they come together, they converge, and one is pushed back into the mantle. So one plate is going back in the mantle and one is going up over the other plate. This process occurs or happens at a convergent boundary, but it only happens at two of the types of convergent boundaries. It happens at oceanic to oceanic, and it happens at oceanic to continental. What it causes is volcanoes and ocean trenches, because one lithospheric plate is pushing the other one, and then the top one is going on top of the more dense. So these two processes together are constantly recycling the Earth's crust. Mid-ocean ridge is where new crust is made or born, and at the subduction zone, it's where the older crust is destroyed or it goes to die, and it goes back into the earth, into the mantle, and it melts down. So let's first look at that subduction. What are our clues here that this is actually a convergent boundary? Well, we're going to look for certain things. First, I see that this plate is sinking back into the asthenosphere. Well, that is a subduction zone. That's my first clue. My next clue is I see oceanic crust and I see continental crust. And I know when they come together, it's a convergent boundary. I also see a trench and volcanoes. Those are my other clues that this has to be a convergent boundary. Some extra facts that we might want to know is deep ocean trenches always occur at subduction zones. And it's the process where the ocean floor sinks back down and is recycled. It's where the Earth's crust is destroyed. And it's the subduction paired with the seafloor spreading that keeps us in balance. One is creating new, one is destroying old. And it's a constant cycle that keeps the whole crust and lithosphere in balance.